Yeah, so thanks for coming today. Oh, we have Thomas. Yeah.
Yeah, excellent. Okay.
Um,
Cool. Intellectual ferment. I like that.
yes. That's
Yeah.
great. So yeah, we're working on the paper, and I know Jesper and Thomas said they could help. And actually, Peter Bohr, I'm getting the people who present in these meetings to do like a paragraph who've done a full session, and we can think of other people, but I think Peter actually said that he was going to get you to help with his, Jesper.
Yeah, I had contact with Peter. Yeah.
Yeah,
I will write a sub-paragraph about the latest article.
That'll be
He will
great.
write something about the infrastructure and
Yeah, cool.
yeah,
That'd
we
be
divided
great.
some work.
Thank you so much. Yeah, and you'll, if you want to, actually, I know if you want to present some more of yours, and we could, we could let you have, we're going to have each person, if they want to contribute, it's going to be a paper, a working paper, and we kind of going to have almost like little collection of abstracts, kind of try to tie them together though.
Like vignettes of the current state of the art, something like that.
Exactly. Yeah. Something like that.
Yeah. Happy to contribute.
And if you want to present some more of your program today, I think we have time. So
okay.
Yeah.
I've been working with Zoltan on a tubulitis project I mentioned briefly, and I mentioned to him yesterday that we may want to involve this group, and he seemed amenable to that. So
cool.
That gets a wider audience. What it does basically for transplant kidney, and which is, I guess, germane to this group, is it grades and identifies tubulitis, fully automated, which is, of course, can be a time-consuming task.
Oh yeah.
So
yeah, it's awesome.
So one thing that you presented last time that I just want to reemphasize the importance of. When kidney people present what they're doing, they always talk about their lack of self-confidence because the cancer people are so much better in every way. And what Yul said last time is he thought that the precision kidney medicine people were actually ahead of the cancer people in some way.
Yeah, I think the targets are better. Yeah.
So that's a very important message, and we got to get the kidney people to stop, apologizing for their situation in the world. If only they were in cancer, then they could really respect themselves when they look at the mirror in the morning, and that's just not true. They should be proud of their kidney status.
Yeah.
I think it's the same for AI work, actually. There's a lot going on in the kidney field now.
Exactly.
And the things that I see in the oncology field are almost always the same, because it's a tumor. And yeah, there's just not that many ways to investigate a tumor, I think. There's molecular analysis and recognizing a tumor by AI. So yeah, I see a lot more interesting things in the nephrology field than now in the oncology field. For instance, at USCAP, it was a little bit disappointing, to be honest. I was there last week.
Yeah. The
not
challenge I see with kidney is that even though there's many potential new AI things for diagnosing and even coming out with prognosis, from the clinical management repertoire, nephrologists have a much more narrow repertoire of silver bullets, right? We need a lot of, so hopefully this research will allow generation of small molecules once we can target novel receptors and pathways. That's the hope, that KPMP pulls out novel targets, because right now it must be very unsatisfying as a clinician to just have to deal with watchful waiting.
Yeah, or
steroids. From that we can learn a lot from the oncology field, I think.
Yeah.
Because there's a lot going on also for the immune checkpoint inhibitors, a lot of different immune checkpoint inhibitors being developed. Small molecules. Yeah,
and I have to think that, just given the last 3 years of data from KPMP, new cell types, fundamentally new cell types that are morphologically the same as existing cell types, but they seem to have a different metabolic trajectory. We're finding different pathways in those cells. I have to think some of those pathways are opportunities for targets.
Sure.
That's an awesome thought. Yeah, that's amazing. Yeah. And it costs so much to develop new drugs in so many years. If we can speed up that process, it'd be that would be a huge.
Absolutely. Like, you know, when we moved into Pfizer's campus here, and I just know this because the person who used to work there became kind of the custodian of the site. They had a small molecules division that had a library of 1 million chemicals.
Wow.
So it's not even a matter of organic synthesis. They have these large pharma have libraries. It's a question of figuring out which combination of these small moieties, lock and key, fit the target. But first you've got to find the target. Once you have a target, there's a very good chance there's an existing small molecule that already has been synthesized.
That's a good point. Yeah. Wow. Yeah, getting this more to even the molecular level is going to be crucial.
Yeah, well, if you could tell us more about the Tubulitis project, Jules, that would be great. Yeah.
So one thing, I mean, you can tell yourself about the project essence. The purpose of the project is to get primary data to the investigative community as quickly as possible. KPMP has already stood up a website and has turned in over 100 subjects or participants' data. It's de-identified, but it's all there, which you can download. So it's already delivered on the promise. There's that data, which is curated by acute kidney injury or chronic kidney disease patients, has the whole slide images. It has, in many cases, the transcriptomics, proteomics, metabolomics, single cell analysis. In some cases, when possible, there's enough tissue, multiple modalities.
Wow.
Codex for each, because the biopsies get spread out to multiple tissue interrogation sites. That's freely downloadable right now.
Great.
It's awesome.
Also for validation studies, it's very, very nice.
Yeah. I mean, it's what we've put on the web already is an amazing trove. And the second 5-year tranche of that, assuming it gets awarded, will allow us to increase the number of subjects from approximately 200. We're hoping to as many as 1,000, which is a pretty powerful cohort for discovery. And what's very encouraging is even though the data for transcriptomics, metabolomics, and so forth have come from multiple sites, the upregulated and downregulated genes are consistent within patients and disease class. So we know that the techniques that are being used now are reproducible. Whereas if you turn the page back 1 or 2 decades to remember spotters that would make microarrays, you might not remember, but the error rate of early high throughput genomics was as high as 10%, which led to an extraordinarily high false discovery rate for both posterior and frontwise probabilities, type 1, type 2 error, if you would. That's going away. And we used to have, issues with 3' bias. That's largely gone away too. So it's just an entirely different era where the consistency of the data is speaking for itself. So the last step is really just for investigators to take this data and start figuring out targets and small molecules. Way faster than any translational development cycle would have been in the past. So one would hope in a few years' time, not the 20 or 30, but maybe five years' time, we would have some, phase 1, phase 2 clinical trials of new molecules.
Yeah, would be great.
That's awesome. Yeah, I meant to ask you or Laura Barisoni, are there any transplant specimens in the KPMP?
I'm not sure. Again, that's not the criteria for inclusion is acute kidney injury or chronic kidney disease. So certainly as a transplant recipient, you could have either of those.
Yeah.
I'm just not sure if that was specifically excluded because it could be a confounding variable because of all the immunosuppressives, right? That could change the molecular trajectory. I'm not sure. That's a great question.
Yeah. Because, that's what,
I can pose that to our group. I'm sure our study coordinators know that just like that. I just don't know the answer to that. Because the inclusion criteria took over a year to make. It's because these are research biopsies, which has never been done before. It's it's a majorly invasive procedure. It was considered unethical before, right? To just do a research renal biopsy. But we got it past the IRB because the subjects are willing.
Yeah.
They're not doing this. They're doing this for science, which is incredibly generous.
Yeah. I mean, that's true because I always got the question, I still get it a lot, is we need to use the normal control for this, work up this stain, or we need to work, or, to do a variety of things. But I say, well, we don't really have normal per se, you know what I mean? But that was one great thing about KPMP is that I think they have a large number of normal, quote unquote.
We have a growing number of normal controls. We do.
Yeah.
These are patients that are not even patients then, just people who underwent a kidney biopsy. Do you understand that?
No, they're normal controls in that they're so that in other words, we got biopsies in the quiescent or recovered phase where normally a biopsy would not be indicated.
Okay.
But so
these are patients with a specific kidney disease. Then.
Exactly. So they do have some. The other thing we have normal control, of course, is from autopsy tissue, where people, young people that died of some other cause.
Okay.
But autopsy tissue is never as satisfying as fresh tissue because of the very quick process of autolysis that takes place. So it's you wouldn't use those. Morphologically, they're okay, but for molecular, probably not so much. And we haven't done molecular on the normal controls, but for morphologic comparison, they've been very helpful.
Checking out the website of KPMP to see if I can download the slides.
Some of them with like the transcriptomics requires a data use agreement, just that you won't publish it without going through the editorial board, but it's still, all of it's still freely available. But most of the data is directly downloadable.
Yeah, that's very nice. SVS format, I see.
Plus, there's also the DPR, which you have to, the Digital Pathology Repository, which has even more information.
That's also freely downloadable, or?
Yes. Yeah. And then there's also, we just got access to the software. So there's a portal for crosswalking the genomics and the morphology with the cell by gene tool.
Wow.
Check it out. It's a great reference. Yeah,
it's a very powerful discovery tool.
That's really awesome. Well, did you have any, would you mind showing us some more of your, I know you showed me a really nice demo of analyzing a kidney, and I think, it'd be great if you had if you wanted to show us any more of that.
Sure. I was just in the process of making a high magnification pipeline.
Oh, cool.
So no guarantee that this is going to work, but you can just see how I build pipelines behind the scenes. And this pipeline happens to be for tubulitis, which is perhaps something germane to it, but it's a coincidence. I'm working on this for Zoltan, so it wasn't because of this particular call. I'm just trying to get him more pilot data, but I can certainly share this. Let's see if
for sure. Thank you. Yeah, I know Jesper and Kim and Thomas would love to see that. And thanks for joining, Thomas. And June was on earlier, but
yeah, happy to be here.
Oh, thanks. Yeah. And thanks for offering to work on the paper. We talked about that a little bit, so we're going to be in touch on that.
Yeah, sounds good.
Thank you.
Get this off the screen.
So it's very nice. I see that the KPMP has 1100 all slide images available, free to download. So that's
Yeah, and there's more
yeah,
coming.
fantastic.
There's a lot more coming. So I've already generated a k-means pipeline in this. And this is the preparative step to doing clusters of clusters. So what I'm doing now, and I sort of did this last week, but this is the literal process. The initial pass generates 16 k-space features from the overall histology. That's just an arbitrary number. Okay, so this looks like it's one of the foreground ones. Because it's the k-means works by initial random seeds. So you never know when you make the first model which color is going to be what. So this is the looks like the inflammatory cells, at least some of them. Did a good job. See how it excluded pretty much everything in the tubule? That's a really good sign.
And did you do any annotation before you did?
No, that's the whole point of this. There's no
Okay.
ground truth mapping. That would be too time consuming. The only thing I've done is I've selected regions that I think are representative of like one class or another, but there's no painting or circling. That would be excessive. That's
How are
certainly
the
a pretty
features
valid way
extracted
of
here?
validating an algorithm, but that's not how this algorithm works.
How's the feature extraction? How is that done? It's not deep learning, this.
Oh, no, it's not deep learning. It's a textural operator where it generates a local texture and then apply, and you can't do this in Fourier space. That's why I think it's taken so long for the machine vision people to even adopt this, because everything has gone to frequency-spaced analysis. And when you look at the orthogonality of looking at local kernel textures in frequency space, you do get an autocorrelation, but it's a single pixel in the FFT, which is unusable, really. So I have to do these calculations in the physical space, in the spatial domain. And so what the algorithm does is it basically half steps at the Nyquist, which is half pixel stepping, and then compares the texture of the template to the image using all the degrees of freedom and rotations, which is basically a form of augmentation, if you think about it. And then it shifts the pedestal and the dynamic range as a further form of augmentation and looks for the best figure of merit, which is the minimum absolute value when you subtract the template from the substrate part of the image. And I apologize if that's too technical, but for those of you that do machine vision, that should have made sense. So basically, it's a template matching algorithm where it seeks to, for any given location, compared to the template, find the best figure of merit when rotating and translating the template for all the degrees of freedom. And you end up with a heat map of the goodness of fit of that textural template to that location. So this was, for example, a template I'd made for one of the darker lymphocytes. And you can see it's identified, and things in the HSI space that are closer to white means it's close from the H, the S, and the I perspective, so it's whitest. So in other words, the closest to white is good, anything black is a non-match. So what that means is it's thinking in here, this is probably a lymphocyte, which maybe surprises me, but
Seems to be the case, yeah.
it must be, because it has a
little bit lower, I think, yeah.
Oh, this one, yeah.
Yeah, that one, yeah.
Yeah, so.
And
I
below,
wouldn't have
there's
thought
also
that.
one.
Yeah, it's so
That one,
it's yeah, so it's working. But again, this is first pass. What I'm doing now is assigning colors to the features and deciding if I want to kick them over the fence to the second pass of k-means classification. So that one is obviously a textual operator, mostly for tubular cytoplasm. I don't want that. I'll go to the next vector. That's a pretty nice reticulin type pattern, basement membrane, but it's not associated in the area around the lymphocytes, so I don't want that. So that's interesting. This is a perinuclear vector, but it's not specific. It's perinuclear to all nuclei. So again, not interesting.
Like an edge detector. Yeah.
Edge detector. Another edge detector, not interested. Tubular cytoplasm. So all these are good to know. You can say, look at this. Edge detector favoring lymphocytes. I'm going to keep that one. That's just cytoplasm. Tubular nuclei, pretty specific. Again, I don't want that. Another type of tubular cytoplasm. Basement membrane, don't want it. Interesting. I gotta change the color to see what it's doing because it's blending in with the. No, I definitely don't want that. Or basement membrane. That looks good. A little bit of false discovery, but it really has. So this is gonna be interesting. This is where the second pass of k-means is gonna help. So I like this one, but it's not pure. But because we're going to go through a second pass of k-means, it should be helpful. So I basically got the features of interest that I want. Interesting, though, that these cytoplasmic areas in between didn't show up. Let's see if figure out why that is. Oh, maybe because it's small areas. I definitely don't want that. Definitely don't want that. Just going back through a second time to make sure I didn't miss something obviously useful. That's marginally useful, but I don't think it's going to help. So that actually is useful. I can keep that. I think that one's useful. Yeah. I was wrong about that one. That one's worth keeping.
And taking a step back, just a generic question. I remember taking your course at USCAP of several years ago, actually, and I think you were talking about this technology even then. And apparently, if I recall correctly, it's like this has been around for decades, and the government actually used it like on satellite photos for detecting like bomb silos and roads and things like that. So it actually predates machine learning. Is that all correct? Correct me
Yeah,
if
this
I'm
isn't
wrong.
really machine learning. This is a text. I mean, I should back up. The front end of this is not machine learning. It's a advanced form of spatial-based textual analysis. But now with the advent of standard machine learning modules like XGBoost and k-means, you can take the output of these algorithms and then apply machine learning to clean them up. So this first pass that you're looking at is the result of these vectors. So these vectors are not machine learning. They're goodness of fit to a particular textural map. This is machine learning. And then this is going to be basically a binary sort with k-means on the output of this, where this is looking at features in terms of HSI 0 to 255. This is combining presence or absence of this feature when expanded outward. So this k-means is looking at rank order rows of zeros and ones. 0, the feature is not present at this location. 1, the feature is present at this location. And so we'll go, so I pretty much now have a nice shopping cart to go to pass 2. So at this point, when I render these things, the first image that's going to show up is the nuclei themselves. And I don't want to, this is the foreground. I don't want to smear these out. So I'm actually going to decrease the size a little bit, just so that we get the centroid. So this is the target we're going for. But then what we're going to do is, by looking at the other feature vectors that co-locate with it, we're going to spread them out spatially so that the adjacency is known to the algorithm. In other words, they start out as rings. And then some examples, let's see, the first one's going to be 7. And they're happening in many instances next to the lymphocytes of interest. So because the k-means needs to operates at a pixel level, I need to have these events be spatially smeared out so that they overlap with the lymphocytes. So I'm doing that by taking the events here and making them physically larger by doing a binary dilation function in the binary mask space. So that's large enough they're overlapped. So I'll go to the next feature vector, which is 9. And these can be spread out as well. Again, I'm not going to use these as a target location. They're simply the statistical adjacencies that tell the algorithm there's something important overlapping between this texture and the lymphocyte, where you don't have these events happening inside the tubules. So even though there's some false discovery, the overall milieu is what the k-means is classifying on. So every pixel from this stage, which is classified now, represents a biological milieu. And we can use that milieu to then tell the second pass of k-means, is this like a false positive, or this is a lymphocyte occurring in the biological context that really makes it a lymphocyte, as an example. And we have the final one, which is 16, I think we need to go to. And this, again, this is not the lymphocytes per se, but an adjacent surround that tells you you're in the region of lymphocytes. And I'll spread this one out as well. And that means the final target we're going for is going to be one region that has the feature one by itself. So that's actually pretty good. And I'll kick it over the fence to the training algorithm, and we'll see what we get. And this second pass is usually pretty fast. Oh no, why did this happen?
I was so excited to see what would come out.
Let's see what I did wrong. Too few clusters. It may be the case that I didn't give enough. Let me put a couple more things in here.
So do you know how robust it is against color variation and things like that?
It is, because I'm not doing color, I'm doing HSI space, and the hue itself is transformed from a projective to an affine map by rolling around the red and the violet back to it, and then I wobble the circle of color for fit. So it actually does a number of iterative optimizations to address for color drift as well as pedestal and offset in the dynamic range department. So and again, the other thing is it uses a logarithmic scale as for contrast. So it's only looking at the foreground matches and excluding all the background, which makes it very resilient against different exposures, which is a common problem with whole slide images. Okay, let me throw in, I'll throw in 11 as well. That may help. There we go. Let me clean up one thing. Update modified, have to kill the CMD file. Delete that.
And thanks to Laura Barisoni who joined us today. I was just letting her know that, you know, you're giving us a demo today, and
Okay,
it's great. Yeah.
I'm almost done with cleaning this up a little bit. Let's see if the canyon's working again.
So since it's based on texture, it should also work, for instance, with the silver stain.
It'll work
Yes,
on
right?
any stain,
It's the
but
same, yeah. But
Yeah,
if you would train something on this, you could apply it to the silver stain as well.
well, because it looks at the textures in the HSI space, though, what I found is that you need to run the stain for which it was trained on. It
Okay.
doesn't work across stains. Because it's not looking at a black and white image. It's actually looking at the color information as well. Okay. So I've got that running again. And now that that's running, I can go back to this one on 11 and spread that out a bit. And we'll try retraining it now. That should work. Let's see how it does.
You can play around a little bit with the template if I see it correctly, right? So now it's HSV Gaussian vector.
You can, that's just for the initial, oh, here it is. Okay, it worked.
Yay.
So now what I want to, so there's a lot of false discovery in here, which is fine. I only want one particular class, which I think is going to be the cyan, but I'll turn it all off and we'll figure out what it is. It's going to be cyan or one of the greens. And now I have a filter on the second pass to find one feature. So let's see if it's this one. I think that's it.
Yeah, it might be, yeah.
That might be it as well. So we'll make it.
So the different Ks that might represent the same structure.
Yeah. So that's
Which is also
definitely
something you see in deep learning, I think.
yes. Well, it's because it's overfitting. It's not, or it's over subclassifying. And so the trick is to recognize when it's found one structure but classified it as two things and then brought it back as one. So for example, this lymphocyte here, it's found it. Right?
Yeah, so blue here is the epithelial cells probably.
Probably. So that's the rest of it as well. So I'm going to add that one. So I think at this point we're done. I mean, I could look at the rest, but I think the rest aren't necessarily. No, that's surrounding area to lymphocytes. No, that's part of it. Okay, so we actually did pretty, so it subclassified it quite a bit. So at this point now, if I go to, I think this is enough to do the demonstration. If I pick any other field, like here's a pretty rip roaring. So let's go a little lower power. Why don't you pick a field you want me to generate? And it is magnification specific.
Yeah.
So we'll go back to high power, but any preference for a field?
Yeah, somewhere around the border of the inflammatory infiltrate,
Right,
I would say.
The edge. Yeah,
Yeah,
the
right,
right.
inflammatory
Yeah, like-
infiltrate.
Okay, so this edge,
Yeah, like here.
like that, so we would expect no events, maybe this is probably an event, right? And then all these guys. So let's see how it does. And of course, once you're happy with the performance of the single tile, you apply it to the whole slide image and you get the whole thing classified.
How long does that take, more or less? Have any idea?
Well, the 2 passes have added a little bit of time, but this is just running on my laptop. On the cluster, it takes about 4 minutes, which isn't too bad.
Yeah,
To do the inference on the whole slide image.
Yeah, for smaller biopsies. I mean, if it's a really large biopsy, it'll take longer.
4 minutes, not too long.
But the discovery itself is definitely interactive, which is pleasant, as opposed to sending a batch to an algorithm and coming back hours later. And then I used to always think, well, what was the question I asked? Which is a bit frustrating. So you don't have a problem here. Okay, so the first pass is done. We'll do the second pass as soon as it comes back. Okay, it's running.
oh,
Here's the answer.
Wow, seems pretty
Yeah.
good.
Yeah, you can see that
Actually, I can change
there's
this.
tubular capillary and it's being recognized that there are inflammatory cells there. Yeah,
There.
looks pretty good.
They don't want color.
Yeah.
Found this one.
yeah,
So what do you think? Pretty. I mean, no algorithm is 100% accurate, but
Yeah.
seems to do a pretty good job.
yes, it does.
So here's
Very
a
impressive.
tubule that it should ignore most of these, one would think, and find all the stuff around it. This would be a good test of it.
Yeah, or a glomerulus
Yeah.
to see how it deals with the other cells. Yeah. So there now have been a couple of articles that show actually that these handcrafted features, they have something on top of, they have some predictive value also on top of the deep learning features. So I think both approaches are very interesting, especially when combined.
Yeah.
And of course, this is a lot more explanatory than the deep learning. You really have to go and interrogate the whole neural network to see what is being recognized. And probably a lot of
Yeah,
the
this
features
is-
are
this-
very similar.
This is not deep learning. Right.
Oh.
This is much more explainable because you can see the constitutive spatial
Yeah.
features that are then just being used. So the first pass is just to classify the biological milieu. And then the second pass essentially is classifying adjacencies, like, you know, one class versus another. So it derives confidence that you have a lymphocyte because it's a lymphocyte arising in the setting of other vectors versus not, you know, tubular vectors. So it's context. So it's, in some ways, it's doing what a pathologist does. It recognizes, he or she will recognize a foreground structure because it's arising in the right setting. So this is done. And we'll run this now. And that just did the smears, and now I'll run the algorithm. Let's see how well it excluded the tubule.
Wow. That's pretty good.
And a couple of lymphocytes that are there still being
Yeah.
recognized.
So this one is real.
Yeah.
I don't know if this is a lymphocyte. What do you think? Is it? It's saying it is.
Sure, either. I would say tubule,
Tubule.
tubular epithelial cell. Yeah.
This one is something, right?
Yeah, I think there's some lymphocytes in the tubule. Yeah.
So it's found that. So I mean, it's not perfect, but it's, as far as comparing to what a human would do, this is pretty close, and it saves a lot of time.
And you could actually use also this to, for instance, to annotate images
Yeah,
as an input for deep learning.
right.
Yeah,
So that's-
absolutely, absolutely.
And then let's say go through the images and say, well, this is probably not correct. We'll get rid of this one manually, like a human AI loop.
Yeah, yeah.
Yep.
Very nice.
So here's another field. This is definitely not proximal, is it?
I would say distal. Yeah.
That's distal. Yeah.
Also curious how the glomeruli do it.
Oh, we'll do that one next. I just hit the send.
I could imagine that this algorithm works very well with contrast. When there's images with contrast, it can recognize the different types of contrast. Like here, the lymphocytes. And for deep learning, there, if you annotate, let's say a whole tubule, maybe it's better at recognizing these bigger structures. So a combination would be very interesting to see.
That'd be a good question to ask. The challenge with this particular pipeline right now is it's targeted for finding one foreground feature versus all the background features. So if you want to identify multiple structures at the same time, you have to run multiple pipelines,
Huh.
which is a small price to pay though for getting this level of specificity.
And you'd run 2 pipelines to detect the tubules and the inflammatory cells, and then look at the overlap to tell where there's tubulitis.
Yeah, exactly. Or you just basically look for the purposes of generating a ground truth map. You generate a mask that just shows you where the lymphocytes are located. There's many ways you can dice it or slice it. Okay, it looks like we're done. I'll run this through the pipeline. What do you think? You're the
Yeah,
nephropathologist.
very nice.
Yeah, it seems to exclude all the regions of the tubules. Also when they're completely overtaken by inflammatory cells.
It's saying that these two are
Yeah, I would say yes.
inflammatory cells.
At least the top
Yeah.
one. The other one maybe not.
Yeah, this one's more debatable, but
And on top you have also a tubule that is a little bit more hard to see.
Mm-hmm.
Center
Yeah.
top,
Yeah.
I would say.
Yeah, I was
And
thinking
also
it had
it's-
messed up, but you're right. I think there's some tubules there.
Yeah.
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 And also in the let's say it's 4 or 5 o'clock, there's also a tubule, I think. And there it recognizes, I think, also inflammatory cells inside the tubule.
Yeah.
Interesting.
So let's see if glomerulus
Yeah.
confuses it, or if it stays sane with.
Especially the
glomeruli.
mesangiosites would be interesting.
Yeah. Yeah.
They look like lymphocytes.
And that'll be a good test of it. I actually in this training set didn't put any glomerular features. So it may,
Let's see how smart it is. Yeah.
which means you have to include, of course, glomeruli to exclude those features, but we'll test it.
Yeah.
It's the same in deep
Well-
learning, you know, if you don't include glomeruli, it starts to recognize probably other stuff there as well.
Huh.
Yeah.
Hmm.
It certainly will recognize all these as inflammatory cells. So it's false triggering on some of them.
Yeah.
Okay.
Well, some are of bone marrow origin, probably. So,
Maybe we are wrong. Maybe these are lymphocytes.
Well, this
I'm
is
sure if you include it in your
this is why
training.
you need to do like immunostains to figure it out, right?
right. Yeah.
There needs to be a biological ground truth at some point. Some of these might be lymphocytes, but suspect many are mesangial cells.
Maybe some podocytes even.
Yeah.
Yeah.
Let's pick a different.
I was wondering what it would do if you went to an area that was all, you have an area there that's all, almost all lymphocytes. And I was wondering what would happen.
Like
you know,
that?
Yeah.
Yeah.
What
Some of
what
those
does it do
areas.
in
Yeah.
that sort of area?
Like this?
Yeah. Sort of
That-
like that. Yeah.
I mean, it applies rules consistently. I would think that the whole thing is going to be yellow.
Yeah. I would think so
Could
too.
be.
Should
Yeah.
be. Let's see. Yeah, the real time of this is very satisfying, you know?
Yeah, the near real time makes it, it lets you ask questions and then get an answer while you remember what the question was.
Yeah, way better than past experiences.
So are you working on ways to export once you get, like, for example, you had a lot of cases you were ready to analyze? You have ways of exporting that data, sort of like percent infiltrate or something like that? Do you have ways
Yeah,
to?
it'll generate a percent of surface area, and it also can generate just binary masks that
Mhm.
can be used like by ImageJ or downstream tools.
Okay.
Because a lot of the morphometrics are not in this, and this application is not meant to be the end all. It's just another tool.
Yeah.
And so you know it'll generate things that can be consumed by other morphometric tools like ImageJ or Definiens, any of the standard or Visiopharm, although those are difficult tools to use sometimes. Okay, let's see what it does with this one. There's your answer.
Oh, wow. It did.
I think there are
Wow.
2 tubules there, at least.
Yeah, it did better
And
than.
they're not being recognized. Yeah.
Yeah.
Right here, you mean this one?
Yeah, on the let's say at
Oh, they're down here.
7, 8 o'clock. Yeah, there.
Yeah,
And also
Yeah.
at 1 o'clock in the
Yeah.
top.
does a very good job. Yeah.
Okay, here's a ideally it should ignore all these things too, right?
Yeah,
Right.
tubular
Yep.
atrophy. Yeah.
Yeah.
I see some T IFTA there.
Yeah.
There should be some.
Actually, these might be inflammatory cells right
Yeah,
here.
exactly. Yeah.
Sure.
Because even if it's not 100% right, if it's largely right, it's still doing the work of generating ground truth that a pathologist would take a very long time. You have to like make a mental decision on each and every cell.
Yeah.
Like making a painted ground truth map of the single tile would probably take me, I don't know, what, 10 minutes, 15 minutes?
Yeah.
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 That's why I said it might be interesting to first run it through this algorithm, let's say, and then with some sort of erase out the things that you don't want and retrain it. There's like some feedback,
Right.
some human feedback in there.
That's a good point. Yeah, that's a
Yeah.
good. Yeah.
And it should get better and better then, I would
Uh-huh.
assume. It's also interesting for the oncology field, this, because they're looking at a lot of these TILs, and
Yes.
there's a lot of effort in AI designing AI algorithms to recognize and count TILs for immunotherapy.
Here's the answer.
Seems to be
Yeah.
right. There's some TF.
Very cool.
That worked very well. Huh.
So you're gonna find a little more challenging field.
Maybe with a little bit of white background. Maybe it's on the edge of the biopsy. Or some there, yeah. Maybe there's a region where there's some artifacts in the lymphocytic aggregate.
There, you mean the,
Let's say on the left bottom of the biopsy.
right here?
Yeah.
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 So this is
Yeah,
a
crush.
part of a kidney that is you're getting into the capsule and stuff.
Yeah.
And I was wondering.
Maybe this corner here?
Yeah. Let's see.
Yeah.
Artifacts
Let's see
there
what
also.
it does with that.
These are inflammatory cells, aren't they? Or is that just hard to say? Or are
I would
they
say inflammatory. Yeah. Maybe with
But
some
even-
nerve sheds there.
Yeah.
Cells
yeah,
in
they're-
the tubules that light up in purple and blue are inflammatory cells.
what was that, Laura?
Tubules with probable, maybe some tubulitis.
This one here?
So no, the image that you're showing on the right side, where you see the purple and the blue in the tubule. Maybe within the tubular cells, maybe some of them are inflammatory cells.
This
Yeah,
one?
definitely. Yeah.
Yeah, that's here.
I would say so also, yeah.
Yeah, that's right here. It found it.
Yeah.
Yeah, you got them. It falls triggered though on a tubular. I mean, obviously
Yeah.
the erosion function, because these are smaller dots, you can make those go away. But it's definitely finding things that look like inflammatory cells inside.
Maybe
the
that one is actually still true. I'm not so sure if there's not a lymphocyte, to be honest.
Oh, this one?
Yeah.
Yeah, well, I guess you could do stains to prove it one way or the other.
But one thing will be very interesting you to quantify these cells and then compare to human quantification. And you know, we use my mother severe, but I think we need to be a little bit more sophisticated than that when we do even the assessment visually to compare to Viper. So for example, we need to define areas of dense inflammation versus areas of sparse inflammation and grade the amount of cortex that is affected by dense inflammation versus sparse inflammation. Because now you can compare a little bit more to a quantitative metric that you see here.
That's true.
Hey.
I mean, that's a really good point. Could you encapsulate that like in a couple sentences? Because you said that so well, and I'm going to forget the new.
So we're developing a deep learning model for the inflammation, but you know the Viper versus the deep learning model is the same thing. As long as you detect nuclei, that's fine, right? And so what we're doing in our study, because when you quantify by deep learning or Viper and compare to human assessment, we will have my mother severe, or we will have percentage of cortex affected by inflammation. But the human capturing the inflammation capture the cortex inflamed, but doesn't capture the density of the inflammation.
That's a good point. So you can have like a sliding window that gives local density.
Yeah, you can have very sparse in 50% of the cortex, and then you can have nodules of dense inflammation. We cannot capture that with the scoring. We haven't done that yet.
Yeah.
So if we modify any scoring and we score the cortex that has sparse inflammation, moderately dense, and dense inflammation, now we have a metric provided by the human that is a little bit more comparable to the metric that you can provide. Because when you do the topography of this, or even count the cells, it will be, I think you need to compare to something more specific than mild, moderate, severe. Because you can have a little bit of cells everywhere, and we call it diffuse, because they are involving more than 50% of the cortex. Or you can have dense area of inflammation that occupies 20% of the cortex. But if you count the individual cells, the number at the end is the same. It's just the distribution is
Yep.
different. So you will never be able to compare to human assessment unless you change the human assessment to something that is comparable.
I think the most comparable is just let a human count all the cells in the whole slide image, but it's a lot of work.
And it's not going to happen because humans also have trouble discriminating between interstitial cells and inflammatory cells visually.
Yeah, immune stainings and do automated segmentation of the immune cells.
But then if you use immunostaining, why use Viper?
Yeah, but I think that's always the question. So if you can do immunostaining,
And so
it answers your question, right? If is it an immune cell or not?
yes, and so this is how
Just cost money. Yeah.
This is how we're building our model, inflammatory model. So we use immunohistochemistry as a ground truth.
Yeah, exactly.
Yeah, the immunohistochemistry, but I guess if you carry out that initial discovery and you show that you can morphologically get substantial equivalence, doesn't have to be 100%, but let's say 95, 98% equivalence, then the computational extraction of inflammatory cells is a surrogate for doing the immunostain.
Exactly. Yeah. And at the end, it does maybe not even matter for the assessment of the biopsy. It's like it's the same as for fibrosis. There, you really have to quantify every fiber, or is a semi-quantitative score equally good at assessment for assessing the biopsy? You have to do a comparative study and look at outcome. The same here, yeah. Does it really matter if it's 98 or 97 or 96%, or maybe it doesn't matter? But we just like to quantify stuff. I think that's the basis.
Yep. So I took an area that had less inflammatory cells. It seems to be, what do we think? Do we agree with its calls?
I would say yes.
Yeah.
98%.
Yeah,
It's
90,
definitely ignored.
yeah, even 95%, I'll be happy.
Exactly. Yeah.
90%, I'll be happy.
You'll be happy.
Probably with 80%, you have a good correlation also. So
Yeah.
especially when you compare it to something that says sparse or dense infiltrate. Yeah, that's also very subjective, of course.
Right.
It's definitely ignoring all the normal tubular cells, isn't it?
Yeah.
Yeah. Well, we're at the hour, but this has been a fantastic session, and I think the recording, the video will be very useful and stimulate a lot of future activity. Yeah, it's great.
Good. Well,
Yeah, great work.
yeah.
Yeah, fantastic. Well
Kidney
done,
is turning
everyone.
out to be a very nice substrate to test these algorithms. And to be very clear, there's a whole cadre now of quick annotation tools that do the similar thing. So this is by no means the only one. It's just the one that we happen to be developing here. But I think if all goes well, pathology should continue developing tools in tandem with what industry is providing, because industry, of course, gives us black boxes. And while those are very useful for discovery, I think we need tools that are interactive like this.
Mhm. Yeah, great.
Great. So, Brad, I guess
Brad, you're muted.
Yeah. Oh, sorry. Yeah. Thank you all so much. And I think in 2 weeks, Lynn Cornell will be presenting on fluorescence scanners.
Yeah,
And
cool.
yeah, so yeah. But this has been great. Thank you so much.
Very welcome.
Excellent.
Thanks a lot.
Okay, and we'll get the video up soon. And yeah, so
Great.
this will be a great resource and encourage even more people to join us here for this intellectual ferment.
Yeah, exactly.
So here's the final parting shot. Found some inflammatory cells between tubules and looks like it ignored all the tubular space, which is encouraging.
Yeah,
Definitely.
great.
Yeah.
Great.
Very, very good.
Well, thanks again. You'll have a nice day. Yeah.
Yep.
Yeah, thanks everyone.
Here. Thank
See
you.
you.
Okay, take care. Bye-bye now.